Hi everyone, thanks for watching this video. I'm Zhuangyan from Peking University, and I will introduce our new work called Collapsible IDA. This is a joint work with Yue, Yangbo, and Zhi. A fundamental problem in causal inference is how to estimate causal effects from observational data. When the causal DAG is known, we have the backdoor adjustment, and when the causal DAG is unknown, we have the IDA framework. IDA means interventional to calculus when the DAG is absent. It is a framework for estimating all possible causal effects in a Markov equivalence class by adjusting for all possible parental sets of the treatment. The advantage of IDA is that the rule for checking whether a set can be the parental set is local, meaning that we only need to know the substructure of the treatment and its neighbors to check the validity of a possible parental set. However, enumerating all possible parental sets may not be efficient in some cases. For example, in this figure, X has 5 undirected neighbors, which means IDA has to enumerate 32 sets, while there are at most 4 unique possible effects. So our work focuses on the efficiency problem of the original IDA. Our goal is to develop a method which can reduce the number of enumerated possible parental sets and the size of each possible parental set. Meanwhile, the rule for checking the validity of a possible parental set should remain local. Our start point is a backdoor adjustment, and here is the formula. If there is a subset Z of PAX satisfying PY given X and PAX equals PY given X and PAX set minus Z, then we have this equation, which means we can adjust less variables. Formally, a backdoor set W is collapsible over its subset Z, or Z is subtractable from W if W set minus Z is still a backdoor set. Ideally, this can be combined with IDA by collapsing each possible parental set after checking the validity. More precisely, after enumerating all subsets of the treatment's neighbors and checking the validity, we separately collapse those survived parental sets. Clearly, this procedure can reduce the size of each possible parental set, but it cannot reduce the number of enumerated sets. To address this problem, we adopt another strategy. Instead of collapsing parental sets after enumeration, we decide to collapse them before enumeration. And this is a schema. If we can collapse treatment's adjacent vertices based on the CPDAG, then we can reduce both the number of possible parental sets and the size of each of them. Based on this idea, we extend the definition of collapsibility to uniform collapsibility. The formal definition is given by definition 2. Let W be defined by this equation, which can basically consist of all possible parental sets enumerated by the original IDA. Definition 2 says that W is uniformly collapsible over Z, or Z is uniformly subtractable from W if for every PAXG in W, PAXG set minus Z is still a backdoor adjustment set. So our next task is to find such a set Z. The roadmap is as follows. We first study when a vertex of X's undirected neighbors can be uniformly subtracted. And then we study when a vertex of X's directed neighbors or parents in the CPDAG can be uniformly subtracted. Finally, we discuss how to construct a larger uniformly subtractable set from those found vertices. Our first result is about when a vertex of X's undirected neighbors can be uniformly subtracted. Theorem 1 shows that W is uniformly collapsible over a vertex Z of X's undirected neighbors if and only if all partially directed passes from Z to Y pass X. For example, in this figure, all partially directed passes from B to Y pass X, so B can be uniformly subtracted. Similarly, A and C are also uniformly subtractable. Therefore, we only have to enumerate 4 subsets. Next, Theorem 2 gives a sufficient graphical condition to check whether a vertex of X's parents in the CPDAG can be uniformly subtracted. It says that if every pass from Z to Y passes X, then Z can be uniformly subtracted from all possible parental sets. Finally, Theorem 3 proves that for two uniformly subtractable sets Z1 and Z2, if one of them is a subset of the undirected neighbors of X, then the union of Z1 and Z2 are uniformly subtractable. This gives a way to construct a larger uniformly subtractable set from the subtractable vertices. Based on these results, we provide our main algorithm, that is collapsible IDA, which is called CPDAG for short. The main advantage of CPDAG is that CPDAG only enumerates the subsets of NEX set minus ZNE. This modification can reduce both the number of possible parental sets and the size of each possible parental set. Finally, let's see some simulations. We use 15 nodes ER random graphs to test our method. The expected degree is ranged from 1 to 5. The compared method is IDA. To evaluate different methods, we use three metrics including the total number of enumerated possible parental sets and the maximum size of enumerated possible parental sets and the total estimation bias. For simplicity, we report the relative value, that is Rn, Rm, and Rb. Basically, CPDAG is better if the relative values are smaller than 1. These figures show the results. Generally, these metrics are all smaller than 1, meaning that CPDAG is better, especially when the graph is sparse. Note that in each figure we plot two lines. The line with squared marks shows the averages over 100 times repetitions, while the line with triangle marks shows the cases where the treatment has neighbors. The line with squared marks is above the line with triangle marks, since in some cases the treatment has no neighbors, and in such cases, collapsing parental set has no effect. There are many related papers. Here we list some of them. Most of these papers focus on the identifiable cases instead of estimating all possible causal effects. There are some interesting topics, such as incorporating background knowledge into analysis. We will explore them in future. Thank you.